So first off, before I talk about StyleGAN, I want to talk about what GANs are in general. I know in the first week, I think Juliet had asked, what does a GAN stand for? It stands for Generative Adversarial Network. And I think I sort of punted on saying exactly what that is. And so now is the time for us to talk about it. So generative adversarial networks, you hear the word generative as a part of it. We talked a little bit about in week one what generative is. Generative means it's making images rather than the other type, which is called a discriminator, which is essentially classifying or determining what type of image it's looking at. So the funny thing about a GAN is that it actually contains both. So it has both what is called a generator, which is a model that is producing new images, and it also has a discriminator. And the discriminator is a part of this model because essentially you have like a game where these two models are playing with each other. And the way that works is that it is essentially the generator is making an image and the discriminator is trying to guess whether that image is real or not. And the way that you hear, so basically like the training of a GAN is both models start out very stupid, right? So one starts out like very basic. Maybe it understands how, like what the background color of an image is supposed to be. And the generator learns to produce those images until it begins to fool the discriminator. And then both of them get a little bit smarter, right? So then the discriminator begins to understand the difference between things. And then the generator is learning from there. So like the best example that I can think of is something like a forger versus, you know, maybe a bank that's trying to guess whether images are, whether a dollar bill is real or not, right? So in this case, at like the really stupid version, it's like an outline of what a dollar bill looks like. And the forger like thinks it's producing a good job. Eventually the bank is like fooled and it's like, yeah, this is a dollar bill, cool. And then the bank teller takes it to its manager and the manager says, that's not a dollar bill. Like dollar bills look like this, right? And then it moves to the next version, which is like, now it's colored in a little bit. It's still very like graphic, whatever. And this game goes on and on and on. Now it's like got texture and other things. And then eventually it's like, you know, maybe it's something like this. And so that's what we talk about. When we talk about training, that's essentially the training process for a GAN. So both start out like really, both the generator and the discriminator start out really dumb. And then they slowly begin to build up until like you reach a level where it's essentially realism. And I'll show some examples about like how real is realism. In the case of the faces like data set that I've been showing a lot of, like it looks pretty real. In the case of a lot of the work that we'll be probably exploring that is more artistic or other things, it might not reach full realism levels, but it can get pretty close and it can get interesting results. So that's why I sort of stop at this level, right? Like this isn't really a dollar bill, but it's approaching like an almost realism level. And that's about what a discriminator and the discriminator and the generator get to, is an almost realism level. And part of the history of these processes is over the past 5 years, 6 years, it's gotten better and better and better at that realism result, right? So when GANs were first introduced, and they were first introduced in 2014, so it's really only been 6 years of process and progress for this. They start out really small. They're black and white. I think this is probably like 36 by 36 pixels. The next year they got to 64 by 64, maybe 128 by 128. And now we're at a place where like, I think they're just about now doing 2048 by 2048. And I've approached a level of realism that is honestly kind of frightening, especially for some like face data. Part of the reason why face data is so good is that one, I think I talked about this in the first week, it's like actually not that hard to generate faces because faces aren't really that different. Like when we talk about diversity, faces aren't that diverse in reality, right? Your eye position might change a little bit. Your eye color might change a little bit. Your skin might change, size of your nose, maybe you're smiling or not smiling, or your ears are like stick out a little bit more or less. Like they're really actually not that diverse. So we can create really, really close realism with face data. Also, we've been trying to like figure out faces for 30 years in computer vision. So we've gotten really good at what the algorithms are for these things. So now we're at a place like in 2020 where essentially we can create real faces made from like fake faces made from real data. And that's pretty impressive considering 6 years ago, we were producing this little tiny thumbnail that could look like a face, but is like, you could also be like, that's totally a machine made that. So that's the basics of GANs. And now we're going to talk a little bit about StyleGAN. And the reason like StyleGAN is so important is that NVIDIA, which is the company that made StyleGAN, really invested a lot into how do they get realism as well as high resolution. So again, you know, even a couple of years ago, like the high mark for realism was something like this, and that was 128 pixels. And NVIDIA came along and said, we want high resolution and we really want to push realism. And just to remind you, like the point of StyleGAN is that it takes a fake data set, or it takes a real data set of real images, and it can generate a generalization or like a mapping or an understanding of those images, and then produce fake new results. But what I mean by understanding is not like an understanding like you or I are a human as like that's a face. It's more like a machine can understand like faces look like this. They have like a certain shape. They have a certain texture around this position. They have hair, and hair looks like this. Like they don't know it's a face. So you couldn't say like, hey, StyleGAN, like change the eye color. That's not something that StyleGAN knows. There's ways to manipulate that I'll talk about later. But this is basically like it's a big space, and it begins to understand features and types of features in a way that makes them reproducible at a realistic level. And again, like a lot of this requires training data, right? So the faces that we've shown in previous classes from this model were trained on, I think, about 70,000 faces pulled from Flickr. So it had a lot of data, and it trained for a long time on that data. So it learned a lot from that data, but like it required a pretty big Herculean effort to make all that data. Like as I'm sure you've seen running your own scrapers, like would take a lot to create 70,000 well done images that are scraped from the internet and cropped the right way. So a lot of work went into just producing a really great data set to make StyleGAN. And the output or the input from this, and I think I talked about this a little bit last week, but like we'll talk a little bit about latent spaces. But essentially StyleGAN produces a latent space, which is, I describe it as like imagine a 3-dimensional space, and then it's 512 dimensions of those. Our brains can't really imagine anything more than 3 or 4 dimensions, but essentially like imagine a dimensional space, and that any point inside of that space is a image, and it correlates to like images that are in this quadrant are more closely similar for various reasons. And as you move up or down the space, you will like sort of see that a different feature is exposed there. And that's not exactly how it happens, but like that's the best way to sort of think about it. And if you think about it that way, it helps explain certain techniques that we're going to show later in the class. So again, latent space, you'll hear mathematicians describe things as high dimensions. That just means it's more than 3, which means it's hard for us to think about. So yeah, it's worth thinking about. Julie, do you have a question? Yeah, go for it.
I just wanted to jump in. So for example, for certain data sets, like a latent space, the adjacent vector could be just like the difference in color or something.
Yeah, exactly. And we'll look at some stuff like that where some people have mapped the certain vector, like basically a line through that space that could do things like make someone smile versus frown. So some of that work has started to be done, and it's like an evolving field to sort of figure that out. This is so again, like I described this space in 3 dimensions. This is a 2-dimensional space, and maybe it sort of helps you understand how to think about this, right? So each of these numbers is mapped to a color, right? So you'll see like all the 7s are over in this region. All of the 1s are over in this region. And that makes sense, right? Because 1s and 7s kind of look similar. So it makes sense that they're close to each other. Whereas a 6 is maybe all the way on the other side, or like, you know, a 3 is sort of in the middle here. And this is sort of a drawing of that. If you were to pick a different point from each of these spaces, you would get a different dimension, or you would get a different image back, right? And this is sort of mapping like, if you're in this far left-hand corner, which may not actually be in the far left-hand corner, but if you're here, you're going to get an image that looks like a 9. And as you move all the way across the space, you get 7s. And as you move down, you get 1s and 2s. So this is like a helpful way to think about what the model is actually producing. And it's also going to help you understand when we get into things like interpolation, why certain things change the way they do when you move in a certain direction. So this is when I first learned about this, it took me a couple months to sort of wrap my head around. I don't expect you to like completely understand it immediately, but it's helpful to sort of think about these things in terms of like the model is classifying certain features and putting them in a space, and the spaces are sort of connected in an interrelated way. And so here we've got the example between StyleGAN 1 and StyleGAN 2. I think I've shown this now like every week. But essentially StyleGAN 2 came out about 3 or 4 months ago, and it is like head and shoulders above in terms of quality. And there's a couple different reasons why that is. Some of it is like the way they built the network. Some of it is the way that they're training things. There's a bunch of different pieces, but like we've now seen that I think they were about a year apart. We've seen like a really big difference. Again, like every year, like there's a big leap in sort of how we're exposing the, how these models are changing. And now we're getting to a level where, again, like the V1 worked really, really great on faces, but as you could see with my floral data set, it's a little so-so, but now it's doing a great job even with the floral data set. The textures are much better. It represents like sort of leaves, and it understands like petals and other things like a lot better than it did previously. So I'm actually going to show a little bit of difference between how V1 worked and how V2 worked. So this is how V1 trained. And I'll talk a little bit, I'll like rewind and we can talk a little about what's going on. But essentially this is probably over a week of training time. You'll see where it started, is it started in this, can I get to this? Let's see. Well, let me just restart. So see how it started in this very, very blocky way. So the training of StyleGAN started in what was called progressive training. It actually came from a model even before StyleGAN that NVIDIA worked on. And basically what it proposed was that the best way to train things at a high resolution was to start at a small resolution and then slowly grow that resolution. So start at something like 4 by 4 pixels and train it to understand images at 4 by 4. Then jump up to 16 by 16, then to 32 by 32, all the way up to like what could be 1024 by 1024. And that was a way for them to basically like manage essentially what you might describe as volatility. And we'll look at some examples of StyleGAN falling apart, but it's essentially a way for it to balance the size of the model. So if you imagine, you can think about this almost like doing the reverse, right? If you're ever in Photoshop and you downsize an image, and you sort of like are deciding like, how does it represent pixels at a lower resolution of teeth or mouth? And then, you know, so it takes a big image and it tries to guess the best representation. This is doing the reverse. It's like learning small representations of a mouth. And then as it gets bigger, it's like kind of learning almost like a child would, right? Where it's like first grade, second grade, third grade, fourth grade, and you're sort of adding detail as you go up. So this was StyleGAN V1, and it worked really well in the sense that like you saw less examples of these models falling apart. But there were also some issues in that that they go into in their paper, and the paper is linked to in this slide deck if you're really interested. But basically certain features kind of broke down as it did progressive training. So in the new version, what they actually do is this. Now it actually starts with noise. And rather than generating pixels, like pixel blocks, it actually just tries to represent sort of like different areas at a time. So the training is very different in this case. And you'll see it goes through these cycles of like maybe not really understanding what the image is. And now it's hit this example where it's sort of, it understands that like in my floral data set, a lot of the backgrounds are this like beige color, right? And now it's adding a layer here where it's like understanding texture or colors or like mix of colors. And it's soon going to hit a place where it's like beginning to understand the separation of flower petals versus leaves. And it's starting to understand color representations. So it's training differently, and we actually get better results because of this training thing, or because of this training process. And my guess is that what NVIDIA did for the past year was basically throw a bunch of different possible training techniques at it, and it figured out what worked best. And that's part of what's really interesting and weird about machine learning is that like a lot of this stuff, you think you understand it from a mathematic perspective, or like there are a lot of mathematicians who do understand it, but there's still like this gray area of essentially like science by hypothesis and by testing and finding what works. So here we're now at a place where like we almost have things that look like leaves, and like it's still slowly like growing into this place. This is again probably a week or two's worth of training on a single GPU on something like Paperspace. So now we have finally hit a place where like the colors are starting to separate and the textures are starting to get really interesting. And so like this is a really interesting thing for me to see because I've used the first version of StyleGAN so often that to see this version is like, oh, well, now there's actually like, I used to think there was nothing interesting about the first 3 days of training a StyleGAN model. And now I'm like, wow, if I go back, there's actually some really cool results here that are like blobby, but like really textural and like almost Cronenberg-esque in a way. And like, now I could maybe go back and start to look at that stuff, right? And now we've gotten to a place where like, there's some really interesting images like here. Like, so there's some really legitimately like worthwhile things that I can work with here. All that said, like you don't necessarily need to worry about this if what you want to get to is something like close to realism. But I think it's worth knowing that there are some other things that are available to you here if you want to really explore like sort of the weirder space of StyleGAN. So as you're training a model, there's also things to look out for. These are very common things that happen to models. And I've witnessed many people get really, really frustrated because they're like, wait, I thought this was supposed to like create these really great fake images for me. And now I'm finding out that I have a puddle of mess that I don't know how to deal with. The first thing you'll hear people talk about is called overfitting. Overfitting is just a thing that exists in all machine learning models. It's basically characterized by a model essentially memorizes the information you give it. So if I were to give you training data of say, you know, what is it? What was the game? Was it Guess Who, where it's like you see a face and you have to match it with another face? It's essentially that, where the model memorizes faces, and that will always trick the discriminator because it's a real face and it's memorized. But it hasn't done that thing which is what we want, which is generalization, so that it can actually like create fake images that are different enough from the training set to make it worthwhile for the training. The way overfitting works as like a statistical model is like, so basically if you imagine each one of these blue dots as a new image, what you don't want is this, where it's just basically memorizing the images. What you also don't want is where it draws like a really poor line through the middle of everything, because that's not actually like, now this red line is not going to create good images, right? It's not going to create a good image here. It's not going to create a good image all the way up at the end of here. What you want is what's called generalization. And this is a thing where like basically it represents the data, but I could imagine that there being an image here that's really good, or an image here that's also really good. So overfitting happens usually when you have a small data set, which is why I push people to do like 1,000 images. That's about the like bottom end of what StyleGAN can work with. I have an example here of what happens when you don't give it enough images. So here on the left-hand side is a model I tried to train it on, which is on like TV screens and stuff. And you'll see like, see how on the right, it's like pretty fluid in the way that changes. But here it's just jumping between images. And it turns out that those images are pretty closely related to what I already trained it on. So it's basically like, it hasn't really learned much besides like, here's an image that you gave me and I'm gonna spit the image back to you. The way to like sort of look for this when you are looking at your data set as you're training it is something like this. So this is this is like a fake training data set, or fake generate images of my data set as I'm training. And the thing you'll notice here is that like, look at this phone here and this phone here and this phone here. They basically look the exact same. And like, that's a bad sign. That basically means that the model has like learned to memorize a couple of these screens and just keep spitting it out everywhere. And you can sort of see the same thing. Like these two laptops are basically the same. These two weird 60s TV screens are basically the same. So this usually happens, especially in StyleGAN, with a small data set. So it's definitely something to keep an eye on. But I would also say like sometimes people like over worry about overfitting. overfitting isn't the worst thing in the world. Like, if you like how this new like blobby TV screen looks, then great. Like, it actually kind of did what you wanted. What I would say is, going back to these interpolation videos, the problem is that I don't really get that many different results, right? Like, whereas with this, I have like an infinite world of new images. Here, I've got like maybe 20 images to work with. And was it really worth me spending $100 to like train that model if I don't really get anything interesting back from it? Or if I don't get a broad set of uses from it? It's just up to the individual to sort of figure out like if that feels like valuable enough to you. There's certainly some to say like basically running StyleGAN as like a Photoshop filter to create like an image that is like unique or interesting. But I would generally say like that's a poor use of my money. I would expect more bang for my buck out of that. The next thing to worry about is a thing called mode collapse. Mode collapse is like this very complex topic. I have a link in the slide notes if anyone wants to like really dive deep into it. But essentially we like maybe don't really know why mode collapse happens. And like more and more machine learning people are trying to figure out what mode collapse is and how it works. I describe mode collapse as like, what happens is so basically, again, if you think back to that forger and the bank teller sort of scenario, if like, I don't know, if in some cases, like the bank teller had a stroke and just like can't really see images at all, and like anything that the forger draws tricks the discriminator, like it's sort of just like the forger's like, cool, my job is done. Like I can just keep reproducing these things. And that's almost exactly what this looks like in reality. So this is an example of mode collapse from literally like a floral data set that I've trained. And you'll see like none of this looks realistic as like a floral image, but for whatever reason, it keeps fooling the discriminator. And you'll also notice that it isn't necessarily overfitting. Like these two images are kind of close to each other, but like there's still a decent diversity. And this diversity is not based on the training data I gave it, right? Like I never gave it an image that looked like this that it memorized. But part of this is like, and this is maybe getting a little too deep for like this class, but like StyleGAN trains by finding what's called gradient descent. And gradient descent is a difficult problem because there are many different places where gradient descent is at its best or whatever. Sometimes what happens is these models get stuck in one best location, but there are really other locations that are even better. And this is what happens, right? It just gets stuck in an area. It keeps fooling the discriminator for whatever reason, and it keeps generating these images, and you end up in this place that's kind of like Publey mess. I would describe the difference between overfitting and mode collapse as like, overfitting is like, I see where it learned stuff and it like basically memorized things. Mode collapse is like just like kind of pure chaos. And here again, like these are cool images. Like as an artist, I'm interested in what these images are. But again, I would say like my money was maybe not well spent for this. And unfortunately, the thing about mode collapse is it's hard to actually figure out why it happened. There's a certain amount of randomness in machine learning models to do the training work. And sometimes that randomness just hits upon a place where mode collapse happens. So if I retrain this thing again, I might not actually get a mode collapse, and I might actually get the correct like training set that I would expect out of it. So this is a difficult area. The way I also think like, another way that's easy for you to sort of tell if it's mode collapse is like, you're still getting sort of these bounces between spaces. And like these images represent nothing of what was in the training set. But again, they're still kind of cool. Like this is an interesting piece of art. Like this is very generative art, like Perlin noise kind of thing. But I can generate Perlin noise for free if I know how to do it in like P5.js, whereas this model probably cost me $100. So like not worth my time or my money. And it's frustrating when this happens. Like this happens, I don't want to say it like all the time, but it happens frequently enough that like people like who maybe don't know how StyleGAN works or who are doing work on maybe Runway have it happen, and they're like, why is this happening? Is this Runway's fault? Like, is Runway wrong? Or like, did I do something wrong with the model? And it's just like, this is a side effect of certain machine learning models, and it happens. So if this happens to you, like, yes, it will suck that you spent money on it, but don't think that it's like somehow a part of like you doing a bad job. It just happens. And machine learning engineers are learning more and more about how to fix this, but it is something that still happens pretty frequently. I'm gonna do a quick time check. 9:15, cool. Any questions before I go into the actual steps of how I do things? Yeah, so Stephen asks, how early can you detect for it? And I assume by for it, you mean mode collapse?
Yeah, mode collapse.
Yeah. So mode collapse can happen pretty quickly. It can also happen at any time in the model, which also sucks. What I will say is sometimes what I can do to fix a mode collapse is like, say it happens, let's say at the 1000th iteration. If I go back to the 500th iteration and start retraining from that, sometimes that can fix it. Sometimes it ends up you go right back down to that hole and then you're kind of stuck. But unfortunately, mode collapse can happen pretty much at any time during a model. I don't want to like scare anyone off from training because like it doesn't always happen. But it can happen fairly frequently. I would say I've seen it far less in StyleGAN v2 than I have in StyleGAN v1. I'll also say that the technique that I'm going to talk a little bit about later in class, which is called transfer learning, it tends to happen less with transfer learning as well. And I'll talk a little bit about why that is. Any other questions? Cool. I think I can get through the next part of this, which is just like the steps to do your training, and then we'll take a break. So training pretty much needs to be done on Paperspace. The reason is that it takes a long time. Training on something like Paperspace, I would expect to take a couple days to really train a model to a place where you will likely be happy with it. So there are other places you could do training. One of those places is something like Colab, but Colab has like an 8-hour time limit, and it's just not gonna, like, it's gonna be more annoying than it's worth to work on. So training has to be done on Paperspace for the reasons we talked about last week, which is that you need a GPU, you need like solid uptime, and you need like a dedicated space to actually work on things. I posted this video on Slack last week or earlier this week. And these are the steps to like custom train a StyleGAN model. So you'll basically follow these like to a T when you're doing your own work. I put up the videos so that like I don't have to go through the exact, like I don't have to demo it live, but I'll walk you through the steps that it takes to do this work. And then when you actually want to go and do the work yourself, I recommend following the video. The video is up on YouTube. I'll post another link to it in Slack. But I recommend just following this video step by step. It should get you pretty close to where you need to be. But again, if you have questions or you get stuck somewhere, please let me or Leah know. So step one, this assumes you have a data set already set up. So for StyleGAN, you need a folder of images, around 1,000 images that are square and at 1024 pixels. I think we could do a 512 pixel model if you are like stuck at finding high resolution images. But in general, I recommend a 1024 just because it's a little bit easier for me to work with what we'll talk about in a little bit called transfer learning. But that's essentially what you need to do. There is a tool inside this. So you'll need to upload that to your Paperspace server. I think in the example video that I do, I upload a zip file to Google Drive, and then I download that Google Drive file directly to Paperspace. That's my recommended method because it's like the fastest I've seen. You can upload it via FTP, just expect it to be slow and know that you're going to pay a little bit extra on Paperspace hours. But that's what you can do. There's a tool in there that is called, the next thing you're going to do is you're going to upload this to the right folder. All the instructions are here for the folder location and that sort of thing. The next thing you're going to do is you're going to run a thing called dataset tool. And I realize this is super confusing that my tool set is called dataset-tools. And this thing is called dataset_tool. I never changed the name of my dataset tool library, but like they're two separate things. This is how you convert a dataset in StyleGAN to what it requires. It requires a thing called TF records, which is just basically like a simpler way for the StyleGAN model to read in image information. One thing to note about these TF records is they're huge. They're huge files. When you do a conversion of like a 3 GB training data set, the biggest TF record file might become 12 gigabytes. It's insane, it's crazy, but like it's worthwhile because it apparently makes the training go faster. So you'll run this command. Anywhere you see in yellow in the slide deck is something you're gonna need to edit. So in this case, if you have a raw dataset folder that's called hummingbirds, you're gonna wanna like put in that folder name here, and then you're gonna also wanna add that folder name here so that it creates a folder, or it creates a bunch of TF records files named hummingbird. Once you've done that, you're pretty much ready to train the model. You just run this command to train things. And the only two things you're gonna edit or have the potential to edit here are these things in yellow. So the first thing you're gonna edit is your data set. So basically when you run this command, whatever you put in here in this line, you're gonna wanna match here. So this could be, again, if this is hummingbird here, you're gonna wanna make sure you put in hummingbird here. So those two things need to match. If they don't match, you're gonna get errors and it won't work. So make sure your data set names match. And the second thing you can do is a thing called mirror augment. So I think I talked about this a little bit last week. Mirror augment allows you to flip images left to right. So in the case of faces, that's totally reasonable to do, right? Because a left to right face is not that different. In the case of, say you want to generate text, you wouldn't want to flip letter forms or other things left to right. It's not legible, it's not the same data. So make sure that depending on what your data set is, you're doing the right thing here. I don't know that like I think the default is probably to keep it on if you're not sure. But I've generally heard like mixed results from other people who do training pretty frequently, whether or not they think mirror augment is actually good. I think it's fine to leave it on and just sort of see how it goes. So after you run this command, it's gonna just take some time to start building the model and start training stuff. In general, I found with Paperspace, you get a new file, what would be like once an hour. And what those files will look like is something like this. So you'll just have a folder of things called fakes and a folder of things called network snapshots. What a network snapshot, if it ends in a .pkl, that's what we refer to as a pickle file. Those pickle files are what contain the actual model. So it contains the actual math to generate this model. This is what you've been training for. So you'll use these files in the generation steps. When you want to generate images or generate video, you need this file. So the number one thing to recommend is like, especially don't delete the latest version of this file. So they'll always be numbered. They'll start at 10,000. I'll explain why they start at 10,000. But basically they'll start at 10,000, then you'll get like a 10,004 or a 10,008. It might jump by 8s or 16s. I don't remember exactly what it's set to. But essentially you will get a network snapshot with a number. The number, the higher the number is, the later that is in training, the later of the iterations it is. In general, it's probably best just to keep what you get. Like I wouldn't delete anything unless you're absolutely like sure you're running out of space. In that case, the next thing you want to do is you want to look at these fake images. So these fake images correlate to the iterations. So if you open up 1049 fakes, you're going to see images that are generated by this model. And we'll talk a little bit about how to like judge whether a generation is good or not. But this is basically the process that I do while I'm training. I'm just sort of keeping an eye on this. I'll check on this like twice a day, 3 times a day, just sort of see what I'm generating, just to make sure it's not going off the rails and make sure it's not overfitting or not mode collapsing. And again, like don't check every hour because it's not worth your energy. Like this is like a watch pot doesn't boil. Like a watch training set never trains. Like you just like kind of like drive yourself crazy if you look at it every hour. So generally like check in like, you know, every couple hours and just sort of see how it's going. The other thing I would say is like, if you don't think you've seen a new image in maybe an hour or two, or in like, let's say 2 hours, it might be good to check your log and just make sure you didn't get any errors. Errors are pretty uncommon in StyleGAN, but like there might be a chance where it happens. So that's sort of like, that's the best description of what's in these files. There's these other like text files, which I generally never look at. Like, don't worry about them. They're fine. Things you want to worry about are the pickle files and the fake files. So as you first train your model, your very first iterations are going to have a bunch of faces in them. And you're going to be like, why the hell am I seeing faces, right? So your very first version of your training set might look like something like this. And then maybe like a couple hours later, you get something like this if you're training it on floral, and you'll be like, why the fuck are there faces in my data? And that's this thing called transfer learning. Transfer learning essentially takes a data set that's already been produced and it retrains the data based on like your new data set. And what does this do for you? So this actually speeds up your training. It's like hard to, like, I actually don't think that mathematicians really even know, or like data scientists even know exactly why this works the way it does. But my theory and the way that I describe this is like, if I were to ask you to write a sentence in English, like it took you years to learn how to write English, right? And what you learned in order to write a single sentence was actually a huge, copious amount of knowledge around the English language, that to just ask you to write one sentence is kind of like not showing off your full potential of knowledge. And I think the same thing happens with transfer learning, which is like, in order to learn to generate faces, you have to learn to not generate a bunch of other things. You have to learn to not generate, or like, you have to learn about other shapes. So by using transfer learning, we're actually taking all the knowledge that this model has learned, and we're sort of like accelerating the process and saying like, hey, you learned a lot about shapes and other things. Like, now take all the things you learn and add it to this new model. So within a couple of generations and iterations of these images, you'll still have like some faces in here, but they'll slowly begin to melt away. And I find a lot of people actually really like this step. They're like, it's half faces, it's half whatever I'm training it on. That's really cool. So some people actually use these steps and just like explore like making really weird shit out of it. So it's totally a thing to do. It's totally reasonable. But eventually this will disappear entirely and you will get just your data set. And you'll end up with something that looks like this, right? And I think, Steven, maybe you were asking this, is like, how do I judge what the best data, like what the best iteration is? And I've got a couple little things that I've learned about this, which is like, so let's say this is iteration 400, this is iteration 600, and this is iteration 800. Now, I might tell myself that like 800 is always better, right? But that's not always true. Like, this is the artistic part of this work, which is like, as the artist, it's up to me to decide what actually looks good. So if I look at this very first iteration, and this isn't the first iteration, but just the first iteration I'm pulling from, notice how like these lines are like almost straight, right? And plants don't grow like that. Plants don't grow in these like really straight ways. And then here it's like starting to kind of fall apart. I'm getting more flowers in there. And then here I've got something that looks way more natural. So this is a place where like me as the artist, like what am I trying to do with this? Is it something like I want to show and explore spaces where flowers are producing images that aren't like, it's producing images that aren't real, right? Like flowers don't grow like this. Like there's no stalk there, but like somehow the petals are all growing in their own way, which is cool. Maybe that's what I want to explore. Maybe the other case is like, I actually just really want really natural looking flowers and I want to like learn about that. So the first thing I would recommend is do not look from one fake to the next and try to guess like, is fake 404 better than fake 408? Like that is like like you will drive yourself crazy trying to determine like, do I like 404 or do I like 408? Do I like 408 or do I like 412? I would look at bigger gaps. So look at gaps of 100, 200, those sort of iterations. Like you're gonna find much better, it's gonna be much easier to understand what you're looking at and what the differences are between those big gaps. So again, like this is maybe 200 after this one. This is maybe 400 from that very first one. And I can see much bigger differences here between them, right? This one's much more realistic than this one is. And I could go through and point out each one of these details, but it's general. I want like a generalized idea of what this model is producing. The other thing I would say is like, while you're looking at, in this case, what this is 4 by 6, so I'm looking at 24 images. I might like these 24 images, but that doesn't mean that the entire space is something that I would like, right? So I might love, let's say I might love this image, but that doesn't mean that all of my data set has an image I love in it. So it's in general, I want to see like, what am I sort of getting as an overall shape of these images? Now that's not to say like I couldn't just crop out this image and just like show that in a show. Like that's reasonable. It's maybe a little different than I would, it's maybe not the right bang for buck. Like I want to actually show the whole space and like, play with it more often. But it is a thing where like, this is a way for me to explore different options within all these models. I would also say, like, if you love this step, let it train for another 12 hours. Let it train for another 16 hours. See if you like the next step a little bit more. Like, there's always this like sort of inherent like need to just like, I'm done. The model's ready to go. I'm ready to play with it. Like, I want to get into it. And like, that's fine. Like, you can definitely do that. I'll show after the break how to generate images using these models. You can always download a pickle file while it's still training and like use Colab to generate images and play with it. Like, you don't have to be done to be done. There's just like this, like, I think especially when you initially start with like making machine learning, you're like, I want it to be done so fast so I can show and play with stuff. I still feel that way about a lot of my work, but let it train for a little bit longer than you think is what you would normally want. That's just like a couple of tips that I've sort of found about things. Testing and generating images. So in data science world, this is called testing or inference. For us, this is getting to do the artwork, making art things. So this will be generating images and video. In this case, you can do this either on Paperspace or on Colab. The video, which I have here for people, is using Colab. The reason I did it did this video in Colab is because like I haven't talked about Colab yet in this class, so I think it's an interesting way for you to maybe start exploring Colab. But Paperspace also works well. Paperspace is good if you like, are already like, you just finished training and you want to generate some samples. It's a really quick way to actually like generate images. You can immediately look at them. The nice thing about Colab is free. The downside of Colab is it's a little annoying to set up. You'll basically have to download a pickle file from Paperspace, then upload it to Colab. That takes time. Colab only runs for 8 hours. When it's done after 8 hours, it like shuts off your server, deletes all your files. So if you want to generate images the next day, you've got to upload the files again. It's just a little bit more annoying, but it is free. So like, it's worth playing around in. And all the stuff, I explained this a little bit in the video, but all the things that are happening in Colab, you can pretty easily copy and paste into Paperspace and it still works. So again, I won't go through the whole step-by-step process of video. The video covers everything you need, but I will just talk about what the steps are. So assuming you've finished training or are still in the middle of training, basically the other thing I should say is like, if you're on Paperspace, you can't generate images and train at the same time because it's gonna max out your GPU. So if you wanna generate images on Paperspace, you need to stop your model, generate the images, and then resume your model, which is another reason why Colab might be better for you. Like say you wanna pull down one of your pickle files, bring it into Colab, play with it there while you're still training on Paperspace. But you're gonna run one more command. You're gonna run a command that is called run generator. You're gonna use this code. Again, anything in yellow is a thing you can change. This network equals, that needs to point to your pickle file. So whether it's in Colab, which I explain how to grab that link, or whether you're in Paperspace where you actually need to figure out your file path, you'll wanna point this to your pickle file. The next thing is called seeds. Seeds are how many images and what type of random images do you want to generate. Again, this is better explained in the video, but essentially seeds are, if you've ever used generative art or like processing before, there's a thing called random seed. This is essentially a randomized seed. So if I put in 1 to 25, I'm going to get back 25 images. It'll be the first image, second image, all the way up to 25. If I run this exact same script on the exact same pickle file, 1 through 25 will always match up. So they call it a seed because that means it's like, even though it's a random number that's generated into that vector space, it's the same every time. So your seeds will always match up, which is helpful in case you want to try some things like playing with truncation. I'll talk a little bit about truncation in a minute. Truncation essentially says, how realistic do you want the image to be? I have some video examples of that. 0.5 it tends to be the number people use when they want a realistic image. 1.0 tends to be the one that people use when they want a weird image. So I generally default to like 0.7 just to sort of see what I get. Once you've generated images, it's pretty easy to generate interpolations from there. There's another line of code that you can do to run what's called a latent walk. The way that I work is I pick out my favorite seeds from this, and that means I might download them and look at them and pick out my favorites. Then I plug those seed numbers in here, and it generates interpolations between those images. say I really love a blue flower and a yellow flower, and I can interpolate between them. Another fun little trick is if you start with a seed number and end with that same seed number, it will loop, right? So this image is always going to be the same, and this image is always going to be the same. So when your video comes back to the beginning, it's going to loop. So this is a cool way if you want to make like an animated GIF that is always looping. This is a cool little way to do it. You also want to pass in how many frames you want. This might depend on how many frames per second you want. If you want like super resolution, 60 frames per second, you'll want a really high frame rate. I generally do low frame rates just to sort of see what I'm getting, and then I might do a higher frame rate if I want something like 5 minutes long or whatever it is, that sort of thing. Truncation is the same. The last thing you'll do is you will generate a video from these frames. So this just produces single frames, right? And then you can use FFmpeg to generate a video from all those frames. This is the FFmpeg command. I explain a little bit in the video how this works, but in general, all you'll want to do is change the path to point to the images you're trying to generate, and then you'll want to give your video a name. So that's generating it. It seems surprisingly easy, right? Like this was 5 steps total to go from training to making a video, and yet we know how actually hard that is. This should be pretty straightforward once you actually have a model trained. But if you ever run into issues, let me or Leah know, and we'll definitely help you out with stuff. So some advanced and/or advanced-ish things to think about while working on things are truncation. So as I said, truncation is a StyleGAN parameter that looks at realness. This is a video that goes from, real to unreal. So this is changing that truncation level, probably for something like 0.25 all the way up to 2.0. So you can say like this image is not, like those are not super flowery shapes. But in this piece, it's kind of hard to tell. So what I'm going to do is I'm going to show you the horror show that is doing this to faces. So you can see as you get to that edge of like unreal, it gets really creepy and ghost-like and other things. Depending on your data set, different truncation levels will mean different things to you. So I'll show that one more time. So this is probably like 2.0 out here. It's getting really weird at that end. Next things to think about are like, this thing called multi-data training, multi-data set training, or looking at video inputs. So this is more about like, what is your input? What is your data set? Do I want to play with different types of data sets? These images were all generated by starting and training on one data set, and then training for a little bit and then stopping it, and then training it on a new data set, and then training it on another data set. Like this one, I think goes through 3 or 4 different iterations of different things. I think it started with Pokemon, then they added Simpsons, and then they added other things, and it gets pretty weird at this point. This data set was, there's a data set of anime faces. So someone started training with anime faces, and then they trained like portraiture art. So in this case, this is like maybe a couple iterations of portraiture art on top of anime faces, right? So like it keeps the big eyes, but you start to get like more painterly textures. And this is further along in the training where it started with that anime face, but now it's gotten way more into the sort of painterly textures as well. And in the slide notes here, like all these pieces are referenced on Twitter. So if you want to go back and like sort of look at what the artist is doing, there's more stuff there as well. This example here is actually, this is like super advanced level, and by advanced level, I mean, I haven't done it yet. So like, I can't necessarily help you just yet if you want to do this. This is actually mathematically adding 2 models together. So this is a model maybe trained on Japanese art. And then this is a model that, I don't know, maybe was trained on Tron or like 3D things. And like using math, they literally add these 2 models together, and this is what the image is in the middle. So models are essentially just mathematics, and you can literally do addition, subtraction, any number of things. So this is called SWA, stochastic weight averaging. So it's literally like averaging these 2 weights together. Weights are essentially how a model is described. So if you ever hear anyone talk about that, that's what they mean. So this is pretty funky stuff. it's a possible thing to play with if you want to. Secondly, let's talk about videos. Videos are an interesting data set, but I've found some issues with them. So this is a video of me working with a beach scene. So all I did was take the video of the waves crashing against the beach and use that as a data set. What I think is really interesting about this is like then animating your latent space interpolation is it's sort of like a disruption of time. It's like shifting and like moving back and forth in time in a really interesting way. This is like a great example of using a data set and like having it work well. Another person who's great at this is Kishi Yuma. He's a Japanese artist. I think a lot of his StyleGAN work is using video. He just did this piece with Nike that I think is really cool. I'll try to find it and link to it in the chat. But essentially, like, this is a video of someone doing something with their hands, and then like playing it back through StyleGAN, you get different results, and you get that StyleGAN morphing kind of thing with it. So it's a totally reasonable option to think about. Oh, I don't have my, okay, I have an example of Blade Runner where I did this with Blade Runner. And for whatever reason, I didn't put in these slides. So I know James, I think, who is a little sick, I'm probably not going to talk on camera, or I won't make him, is asking about like, can I take video from like my favorite movie and put it in StyleGAN and see what happens? And in general, it's tough. I would say that like in the case of this, where it's like a very clear data set-y kind of thing, where it's just hands, or in this case where it's just waves, you get pretty decent results of it playing it back. It's almost like this memorized those images, but it did it in like a good way. I find that the longer your video length is and the more like different types of images are in your scenes. So example, you take like a movie that has both a street scene and a like close-up people talking scene, you're gonna get some really messy results because StyleGAN isn't really set to like work with diversity of that kind of range. One thing you could do is you could take a small scene of a movie and then mess with that and see what happens. Or you could go through an entire movie and only take out the scenes that are people talking, and you might get something interesting out of that. In general, you have to play with this to sort of see how you don't descend into just pure like murky like garbage. I'll post an example of one thing that I tried. It was in StyleGAN 1, and I feel like it didn't work as well as I expected. StyleGAN 2 might actually be better for this, and I don't know that I've seen really anyone do it yet. So worth an example. Let me guess. Julia, are you saying some stuff? Oh, Obake equals ghost. Cool. Okay. Oh, yeah. Okay. And James posted the video example here. So like there's some really cool stuff worth exploring. I will post some links inside of the Slack later so that you can sort of see how video examples work. But the nice thing about video is very easy to pull a data set from. I'm happy to post some code about like using FFmpeg to literally take a 1-minute video and split it up into individual frames. That's a really nice way to generate a data set. It's just you get a certain element or a certain style of StyleGAN when you train it on that. So just be aware of that. You won't get anything where it's generating like brand new waves. It's going to sort of generate, it's going to sort of like learn how waves work and stop. And sort of like, you get this experience where it's like, it's not really doing it in time, but it is sort of like, it hasn't memorized, it hasn't created anything very new, I would say. Okay, so projection. I'll talk a little bit about how projection works. I showed an example of this in week 1. It was this creepy little thing where you push Mario into the latent space. It's creepy. AI artists love creepy things. An example of me doing this is actually like, here is Oprah being projected into the space. So what is projection? Projection is essentially, we know that the StyleGAN latent space has a lot of images in it that we will basically never find. So what projection does is it says, I have an image. Can you find the closest representation of this image in the model? So what it's actually doing is, you see it starts with what is called the most average woman in StyleGAN. And it tries to like basically figure out how to get closer and closer to the right image in that space. Now what's interesting about this is that, you know, that woman kind of looks like Oprah, but doesn't look like Oprah very much. Like, I wouldn't say that that is Oprah, right? Like, I wouldn't show you that image and be like, who is this? But you can see how it closely matches the image that I gave it that is sort of Oprah. Now, what's also cool about this is now I can get the latent vector out of this. So I know the vector that this produced, and I can do it for a couple other celebrities. And now I can start to animate between different celebrities. So this is Oprah to Jennifer Aniston to, God, I'm totally blanking on names right now. Anyway, I'm bad at celebrities. This is the guys that run SSHH. I was like, what celebrities do you like? This is Britney Spears at the end, I think. And it goes back to Oprah. So like none of those images were actually those people, but you can kind of make out like how it's supposed to represent it, right? And in the case of, you saw that I posted that video that uses Unit. So I use this as an input from Unit. So this is how I converted those people to grassy faces. So you can start to see like, this is an interesting way. I think Leah, you were asking me, how would I go in and like, say I want exactly a yellow daisy inside of my model, you would use projection. And the case is like, you might not actually get to the perfect yellow daisy you want, but you get to something close enough for it. So the problem is with like projection is like, you're never gonna find the exact image you want, but you could get pretty close to it. So it's like, I think Leah, your question was like, I want the exact image that I have in my head. And you may never find that inside of a StyleGAN model. The other way to do it is to brute force generate 10,000 images of your latent space and just sort of go through them one by one and find the one closest to it. It's kind of like up to you to try either of those methods. The last thing I will talk about is feature manipulation. This is like definitely advanced level. Like I haven't done a lot of work in this myself. And I think most of the feature manipulation I've seen has been around FFHQ, which is the Flickr model. So this is Mario Klingemann's work. This is basically saying, I want to pull out the style, the vector inside of a latent space that gives people smiles. And then he can go in and make Mona Lisa smile. So this is, the first step is he projected Mona Lisa into StyleGAN, found the closest representation of Mona Lisa in that model, pulled out the vector, and then through another, I'll post the Colab notebook for this, but basically like there is a line or like a curved line through space that generates smiles. And basically using that line, you can then you can manipulate the Mona Lisa image into smiling. And here's another example of this that I did. So if you're familiar with Kehinde Wiley's portrait for Obama, I basically, I projected in Obama's portrait, and then I went through and made Obama smile. So this actually goes from frowning, which is like the very opposite of smiling, all the way up to smiling really far, and it's like almost like a primal scream kind of thing. So this is stuff that people are still trying to sort of figure out with. I actually haven't seen anyone do this with StyleGAN 2 yet, although it's certainly possible. It's just some of the math behind it is like a little complex. But again, if you want to play with like just FFHQ, like projecting in a face image and manipulating it in certain ways, I can show you how to do that. I think there's another one where like your hair can grow or like other things. Some people figure out certain things that you can do within these models to manipulate them. What are we doing at time here? Oh, we got 15 minutes left. So at this point, like I'm sort of done presenting like StyleGAN work. Your homework for this week is like, obviously, like if you want to do stuff in StyleGAN, start training a model. I know some of you have already started, but if you're really interested in working on this, and I know like Leah's poll, I think just about everybody said they wanted to work in StyleGAN. It's like, now you should have all the things you need in order to do this work. If you're interested in some of those advanced stuff or just like learning a little bit more about certain techniques, just hit me up in Slack. I'm happy to help people as much as possible. I can also point you to other StyleGAN artists who might have like more ideas around things than I do, or like have done stuff that I haven't done yet. Some of these areas I definitely haven't done a lot of work in, so I will sort of be learning alongside you about how to do it. But if you're really interested in something, I'm happy to help out. If you are not interested in StyleGAN, which is totally fine, I do have demo videos up for Style Transfer next frame prediction. So if you have a data set, start working on stuff. I think that would be great to just sort of see people start start playing with things.